Welcome everyone. Finally we have everything we need, and I will open also my notes. So my name is Olena. I work at Ivan, and at Ivan we support and contribute a lot into open source technologies. And today I wanted to talk about vector search and also look at different open source options you have. And we are going to see a lot of different demos. We are going to search for movies. We are going to search for doggies. We are going to look into recipes and also even ask some really boring questions to a chatbot. And all of that using vector search. And also, more importantly, together we are going to talk about the building blocks of vector search. And for the next, how much time we have, we are going to discuss should you use KNN or ANN, what are the different index strategies, what are the distance metrics you want to use, what models you can use, and so on. So we don't have so much time, so let's dive in. And first, let's talk what is actually vector search. And in a simplified way, vector search is a way to find related objects that have similar characteristics. So in vector search, we are using machine learning models, and those models are trained to kind of distinguish the difference between different things, whether it is text or images or audio, and then take some kind of points from that information and organize the data on a multidimensional space. So as humans, we are not really good at thinking about, I don't know, a multidimensional space of 700 dimensions. So let's kind of see it on a very simplified way with 2 dimensions. And when we have kind of those objects or whatever information are being organized there by a model, the model will distribute those objects in a way that objects which have closer characteristics will be put together kind of closer in that space. And what we can do, we can then kind of calculate the positions of those objects and have our vectors. We also sometimes call those like encodings or embeddings. For our conversation today, this is all the same stuff. And when we know which objects are closer to each other, we can kind of compare them and then find similarities. And in the world of machine learning, this is what is called the k-nearest neighbors algorithm. And we are going to use it today. So let's dive into first demo which I have, just to kind of explain how we can use that power for something as a recommendation system. Can you hear me? Oh, it's all good with the sound, right? Okay, cool. Here we are looking for some movies, and this recommendation system is based on semantic search, and semantic search can be done in different ways. Google does it with the graph databases, but we here trying to use something very simple, something which you can use out of the box, and kind of you don't have to be super advanced in those topics to benefit from the semantic search by using vector search, because all the power which we need, we delegate to a model. And the model kind of knows the relationship between the object associations, and it can help us making those connections. So what we are going to do, like in the first demo, and I will share also the code later. So we are going to take the data set. For us, it's a movie data set. We start with that. And then we are going to use the model. And here I'm using TensorFlow model, the universal sentence encoder, to kind of put those objects into a to calculate those vectors, the locations of the objects. And then we take those vectors and we store it in a database. Or kind of like you need to store it somewhere to use it later. And here I'm using, so like not any database, you need a database which actually can then work with those vectors, understand the distances between the vectors, and kind of also work with those optimally, because those vectors are pretty huge. So you need also ways how to efficiently process those distance calculations. So here I'm using Postgres. Postgres is an open source database. You need a PG vector extension, and together then you can work with the vectors. And I guess Postgres, like if you're already using Postgres, you don't really need to go and get another database, vector database, because actually your it's Postgres also like very favorite database by many, so you can use it. So we store the data, we keep it there, and then what happens? We have a user, and user is like, oh, can I watch a movie about, I don't know, a lot of cute puppies? Who doesn't like puppies? So, and we take that phrase, like a lot of cute puppies, and then we again ask the same model, and this is very important. We use the same model because we want to compare apples to apples. So we use the same model, create single vector for the puppies, and then we compare that vector to everything which we have in our Postgres database, and PG vector helps us to find the closest those points in the database. So in simple way, this is the flow which we will see again and again. Yeah, this is actually like the whole architecture in maybe a bit simplified way. The data set I took only one vector. I was taking the description of the movie and then only one. So it's yeah, you can actually technically encode more and combine those, but this is only one. So the dataset is taken from Kaggle. I also created the GitHub repository, so you will be able, if you want later to experiment with this scenario, you will be able to run it on your own. I'll share the links later. It's in JavaScript, and I was glad when a lot of you raised hand when I asked about JavaScript. It's kind of also minimalistic code. So like here we are taking the TensorFlow model and libraries. Usually when you will be working with those kind of models supporting the encodings, you will have also support for the like kind of a library. So here, as I took from TensorFlow the library specifically for the Node.js, because it's kind of like made it like the whole computations are made faster. And I can give to the model a single value. Here I took the description, like the plot of the movie. Of course, can contain some spoilers. This is a different story. But you take that movie, and then we get our vector. So we are getting the list of the numbers. So we converted the description of the movie, some text, into numbers. And this is more or less how vector search works. You take whatever and you convert it into the numbers, and then you work with the numbers, because computers understand numbers a bit better than everything else. So then we can store that information in Postgres. Actually, in Postgres, one thing you need to remember, you will need to install. If you have your Postgres locally, like you are installing on your own, don't forget to install the extension of for PG vector. Also, I will offer at the end, like we'll share with you what you can use for a free-tier cloud option for that if you want to experiment. Then once you have that, you can create the table, and here in the definition of the table, we have a new type of data. We have vector. It comes from PG vector, and you must specify for Postgres how many dimensions you have, so it knows how to compare stuff. And then with that, we can send the data into Postgres. I'm using like PG, so I'm using the bulk functionality here. I will not dive that deep into that, but we want to send all the data processed into Postgres database. And once we have there, then we can take that search phrase, as I said, a lot of cute puppies, and we convert it in as a vector, and then we compare that vector by sending a request to Postgres. And here the request, the select request, has this kind of interesting kind of, I don't know, like symbol. And this indicates for Postgres that we want to use the dimension, the distance metric. This is L2 distance here. So, and this means that we are searching for the distance between different vectors. And we look for 5 closest movie plots by the distance to the embedding from the cute puppies. And if we run it, then we will get those 5 responses from the Postgres database. And some of them don't even have the word puppy, but has some kind of other. Can we keep the questions for the end? I'm sorry, because we started so late and I won't be able to then finish. I added some UI as well. So this works kind of actually efficiently and fast for this amount of data. But actually, I just have 40K records in the data set. So if we will have hundreds or even like hundreds of thousands or like millions of records, then we will have actually a problem, because this is brute force. We take the vector and we compare it to each of those movies we have, which has its limitation. So this is a good opportunity for us to talk about the difference between KNN search and those K nearest neighbor search and the approximate nearest neighbor. And those two, the biggest difference is that the approximate one will start with some limited set of data when looking for the nearest neighbors. It will not really go for everything. It is like, I know that approximately I need to start over here and this is my limit. KNN, the original, the brute force, will be more precise. But often we have to sacrifice that so that it works faster. And there are different types of kind of like how exactly we use that approximation, and there are different index types you can use. Depending on the database which you will have different algorithms already part of the database. And I would like to look at two of those algorithms to give you some examples how it is done, because those two actually they are quite interesting, quite different with their pros and cons, and then you can kind of see like just kind of what you can apply. And we will start with inverted file with flat compression. This is where you take all of your records and then you calculate the number of centroids. So our goal is to divide the set into number of clusters. So we calculate the number of centroids. So I mark those as stars, like you kind of based on where you have your data. So it's not like just randomly. Actually, like strategically, the algorithm puts those centroids, and you organize the clusters around those centroids. And then when you need to search for data, you actually don't really look for all of the data, but you, for example, we look for those puppies. So we calculated the vector, and then we like, which centroid is closest to the search vector? And maybe it's like the green one, right? So, and then we're like, okay, we will analyze only the green cluster, the green part. And that limits the amount of calculations which you have to make. So the one thing in this particular approach which we must remember is that because we need strategically to put those centroids, we can't do it when we don't have enough data. So you really want to wait when you have enough data, so you kind of you have a good shape, good clusters, because otherwise the recall quality, the quality of the results will be lower, because you are going to find not your closest neighbors, but the neighbors from far, far away. And also if you are going to change your data, like with Postgres, for example, we often actually, like our data is a bit more in a kind of change. You change the data and then probably you need to recalculate that, like to re-index the data, so you still have appropriate centroids and appropriate clusters. Couple of properties which we can use to tune this algorithm is the number of those clusters and how many clusters we actually process when sending the request. And of course, like the bigger number of clusters you have means that the portion of the data you analyze at a time will be smaller. This increases speed of the query, but can affect again on the recall quality, on the quality of the results. And again, like you can increase number of clusters you analyze, but that would increase the speed of the query. So you kind of need to find the trade-off. All of this approximation stuff, it's really like with a trade-off between the quality of the data you get and also the speed, and the speed matters a lot. So this was the first index. The second index actually is super, super interesting, and it works quite differently. It's called Hierarchical Navigatable Small Worlds, and the name is so amazing. And what happens here, we create graph with multiple layers. And then those layers are like zoom levels. So the higher you go, the less you have nodes and stuff, but the deeper you go, you have more of your nodes and connections. And then you actually can navigate through that and to find kind of the area where you are looking for the closest neighbors. And this approach I see a bit more frequently in usage because it offers possibility to find stuff faster. It has its limitations. But so here we have stuff for tuning in the index and a couple of properties which affect the speed of the query, but also the speed of the creation of that index. So those properties are M. It's like number of like maximum number of connections per layer, and as well as we have this EF construction, and this is just a kind of a buffer size during the creation of the index, how much it will keep data there. So you can increase those, and this will increase the quality of the recall, but it will increase the time of creation of the index, the size of the index, and this is actually where the disadvantage of this HNSW is that actually it will take more resources. So overall, like between these two, and they both are supported in PG vector, but also they are very, very popular. So they are often supported by other vector databases. So if you want to have a small index and you want to have this faster building time, then use the IV flat. Or if you are resource constrained, so you don't have so much GPU or you don't have so much like space to store that index, then go for IV flat. But if you're looking for better query performance, or you kind of modify those vectors so often that like recalculating centroids you will need to reindex too frequently, then go for HNSW. It's more resilient for the changes of the data. Cool, and I mentioned a couple of times the recall. Recall is kind of how we calculate the precision of our approximation algorithm, because you care about performance, but you also care about like how many of those neighbors which we got as the true neighbors and not like the fake ones. And the recall of 1 means like 100% of the neighbors which we retrieved are the true nearest neighbors. The recall of 0.5 means only 50%. So, and here like you will have to find a good balance, because with approximation algorithms we are working with heuristics, which means that there will be always some errors, and then but you are doing this for the speed. Cool. It was a lot of theory. Let me show the second demo. And the second demo, we are looking into the usage of different types of data. So we have models which understand not only text, but they understand text and images. Or maybe they understand some audio, video, or something like this, and they can be like combined. And here I'm using a set of images from Unsplash, and then I'm using a model which is smart enough to understand the relationship between images and text and kind of like put those together. And this is a clip model from OpenAI, and then I'm taking those images, I'm again putting them into the vectors, and I'm storing that. And right now, for this particular demo, I'm using another open source database, OpenSearch. Really love OpenSearch for so many different reasons, but also OpenSearch is really good at working with the vectors. So, and then we have the same, but just like from the point of view of the search string, now our users type something like, I would like to see a hot cup of coffee or a cat playing in the snow, and then we create that single vector, compare it to everything which we have in OpenSearch, and then bingo, we have some images. From the implementation point of view, you will need, if you ever worked with OpenSearch, you might know it's really super flexible with dynamic data, but you need like in advance to specify that you want to have the KNN index and also to tell the open search that this array is not just an array of numbers, but actually this is an array of vectors of this dimension. And after that, we can ingest the data. Here I'm using Python. Again, like it will be the link I will add, will give you for the code if you want to use it for your projects. And I'm processing the images. I'm taking the image. I have like the image itself, but also have a URL. So I store in the open search the URL to the original image so I can display it later. And I store the embedding, so I store the vectors. And when we did that, now we can do similar like we did before. We take the search request, convert it into numbers, and then we send that request to open search and ask, like, could you give us images closest to this particular vector? And then we can send that request, and then we display the image, and I just visualized, like I visualized the first image out of that list, and I was looking again for dogs somewhere. So this is how you can combine. I think it's actually really allows a lot of powerful things. I think like Trello uses, I kind of feel they use it because like they offer you like you can put some background and actually they take the data from Unsplash, and I'm like, yeah, they're using vector search there because this is kind of like you type what kind of background you're looking for and they give you images. Yes, so both of these examples, what they use to compare, because we need kind of like behind the scenes, what the vector database will do, it will compare different vectors and kind of find what is the nearest. And for this, we have different ways how we are like looking, like which vectors are closer to each other. There are different ways you can actually calculate the distance between the objects in real life, and like those different ways can affect the performance and the quality of the results. So let's look at different things which we have, which we can use. And for machine learning, the list of those kind of distance metrics or distance approaches is huge. Here I selected what I see frequently in the vector search. So the one metric, which is the easiest, I think, for many of us to understand, is the shortest distance between 2 points, which is also called L2 distance. And we kind of use it pretty frequently, but it's actually a good metric when all the dimensions in your data have the equal importance. Because here we kind of like, and I put the formula which you might remember from school or somewhere, like this is like if you have 2 dimensions. Of course, if you have more, it will be way, way longer. The kind of challenge with this, so in this actually metric is pretty good. Like it's resilient enough to the outliers, not too resilient, because if you have really big values, because we are taking the squares of the values, it might have some problems. But in general, it's a good, solid metric. However, because we are calculating the square roots and so on, we are like, this is more computationally expensive than the other things which we will see. Cool. The other one, which is less computationally expensive, quite interesting one, and might remind you of traveling to New York because it's Manhattan distance or L1 distance. And here, assuming that you cannot really go in a straight line with a taxi in Manhattan, you have to make some turns. We are calculating the distance more or less like the straight lines and angles. So it's more resilient to outliers because we are not squaring the numbers here. And also it's way cheaper to calculate. So that can be like if performance super important and you used before L2, you might consider switching to L1 and see if it's still precise enough, because of course it will give you probably less precise distance metric, but it will be faster. Another one which is quite interesting, which is used less, but it actually is super cool to emphasize the dominant features. Maybe you're kind of only carrying like the key features, like a distance between them, and worst case scenarios. And this is called L infinity, and it kind of takes the longest across all the dimensions. So it's used less, but it's I feel it's kind of also has, I think it's mostly used like in image processing and circuit design, but also can be a good choice for vector search. Then we have another one, which is actually by far probably the most recommended when you're working with text, and it's called cosine similarity. And this one is kind of good when you don't care about the magnitudes of vectors. So we're taking the angle between the vectors and we're taking the cosine value of it. And if you have a normalized data set, so you don't have really huge difference in magnitude, or you don't care about magnitude, this is a good metric. The thing that like you can imagine that you can have the same angle, whether the magnitude of the values is very different. So that's why you by default ignoring the magnitude here. But it's really good for high dimensional spaces such as text and like used very frequently for text comparison. And the last metric which I wanted to show is like if you do care about angle between the values, but also you do care about the magnitudes, then you can look into inner product that will be doing the projection of one vector on another. Some people complain about inner product because, for example, comparing to cosine similarity, the cosine will be from -1 to 1, right? So an inner product will be from -infinity to infinity. So you don't have those natural borders where you kind of can say what is the biggest one. So I'll also share some links to the resources you can read more about it and also some kind of studies. So overall, which one to select? Actually, it also will depend which model you use. If you're using the model and they do recommend the metric, like the distance metric, I would go with the distance metric. If they don't recommend, for text I would use probably cosine similarity, but I would also see and compare and try, because this is where it's actually very difficult. It will depend on your data and also like on the magnitudes of the values, on kind of dimensions and so on. So you will have to experiment. Cool, and yeah, so some of those will work faster than others, even though it's not the biggest thing, like changing the metrics might affect the performance, but bigger change in performance I observed when adding some filtering. And sometimes we want to add filtering because we want to kind of pre-filter some stuff so that we have a less corpus of data, but also sometimes you actually need to add filtering. For example, you have some metadata and you have some values like integers, booleans, and so on. So you want to combine doing the structured search and also kind of vector search. And how exactly can you do it together? So maybe we would like want to recommend the movies where the length of the movie is less than, I don't know, 2 hours. So we need to combine then two of the different types of search. And there are 3 different ways how you can do it. The one which is quite popular is pre-filtering. So it's when you apply first your structured filters on the complete corpus of data, and then you take the result and you apply the vector search. And this actually can be a pretty good idea, but it has some kind of dangers. So the thing is, if you apply the structured search and your corpus significantly gets smaller, and then your vector search, you can use the brute force because you lost, like, you can't really use the calculated index of rate. Like you will probably need to recalculate the approximated index if you want to use the approximated algorithm. So, but you can go with the brute force. And if the corpus got significantly smaller, you actually get pretty good because the brute force will give you way higher quality of the results. So that's kind of good. But if you apply the structured search first and then you have a huge corpus, and then you're like, okay, brute force is slow, but for the approximation algorithm, you need to rebuild the index. So kind of like, then it might be not might be solution which scales pretty poorly. So you want to be like careful here. Another approach which is possible is to do the post-filtering. So you first do the vector search and then you apply the structured filters. And here I would say this one I see like less in favor because you might end up with no results. It might be that your vector search will cut down all the things which actually you're looking for in structured search. So you can, like, I don't know, like, it depends, of course, on your solution. Maybe it's actually a good one, but might be problematic. So what, for example, OpenSearch offers, and I see it also in other solutions, is what at least OpenSearch calls efficient filtering, where they actually intelligently go and decide which one to select, pre-filtering, post-filtering, and also they kind of calculate the filter ID, so they do some smart work for that. And probably if you are using a vector database, any of those or something else, look if they offer something like efficient filtering. In OpenSearch it will look like this, like they will put the filter like inside of the KNN query. And this I see, like at least for us, when we have seen some scenarios where the vector search is used so heavily, where we wanted to squeeze everything out of the performance. So this one actually made the biggest difference. I mean, like filtering in addition to vector search. Cool. Let me show one more demo. This one is pretty short, and here I just wanted to show using a different model. So here I'm doing stuff with recipes, and we are taking model here from Hugging Face. Hugging Face is an amazing place with a lot of open source models. Also, you have like really a huge variety of models where if you are not going to get your own model, at Hugging Face you can look for a model which will transform your data into indexes, but maybe which was trained on the data which is close to your domain. Because of course, like this is where the problem can be, like you would like to process some technical documentation, but your model was trained, I don't know, like on movie data set or something else. So like your model will be like, it will work to some extent, but not exactly, because the model might be a bit, like those connections will be not precise. So there's an advantage of going with some kind of a broader set of models and search for something, and Hugging Face is just an amazing place for that. So here I'm actually using a mini model. So the smaller number of dimensions, faster will be your vector queries. And for the database, I'm here using ClickHouse. This is actually a data warehouse, super, super fast, super amazing. And it also, like, it actually very frequently used with some machine learning, like kind of like science functionality. It has lots of different functions, and then it also can calculate the dimensions between vectors. And the rest is kind of same. We are again transforming our search query, and we are comparing that stuff to what we stored in the ClickHouse. When it comes to Hugging Face, and I totally recommend if you are going to use something and looking for those like solutions out of the box, Hugging Face offers like nice, so you can look always for popular models. You can see, like, you need to trust also the model. You don't want to use a cat out of bag. So you want to check maybe like how many people are using it, what kind of discussions are there by community. Also for those people who don't really speak fluently Python like me, I really appreciate that they put some code snippets. So actually I often take that code snippet, like modify it how I need, and then I use it for my functionality. So super, super friendly, I would say, especially when you are beginning to work with those things. I used for this one Parquet because ClickHouse loves Parquet files. I also love Parquet files. With ClickHouse, I created a table. There, ClickHouse doesn't really ask you for a number of dimensions. Just like tell it that you will be putting there some numbers, like an array of numbers, and then I injected the data, and then I could send the request and specify the distance metric and ask, could you retrieve me 10 closest recipes? And the distance functions which ClickHouse offers, the list is pretty long. As I mentioned, it has like so many like generally functions for mathematics in ClickHouse. So yeah, you can select whatever you need here. The disadvantage of ClickHouse, I mean, to some extent, it doesn't have right now, like all the approximation algorithms are experimental. However, ClickHouse is a data warehouse, it's a columnar database. So by default, it works so fast that I wouldn't be surprised that brute force by ClickHouse will be faster than approximation algorithm of other databases, just for the sake, like it's not your normal OLTP database, it's OLAP database. So, but if you have a data warehouse and if you're already using ClickHouse, you can use the vector search. So this is the kind of usual, like using the, I would say, simple models, but we can do something a bit even cooler with the vector search. We can build some chatbots using large language models and combine it with vector search. And why would we do that? The thing is, the large language models, and we are using them very, very frequently, and they are amazing. I mean, who wouldn't like to spend their free time chatting to ChatGPT? But well, so but they have some disadvantage, because the training of large language model takes time, and actually it's also quite expensive. And then to refine or retrain the model is also expensive. So you might go for it for your particular case, but you also might want to add some data which you would not really use as a training data set, some kind of personal information about the users. Or maybe you want to add some real-time context, like from today, about that. Or maybe some relevant factual information that is not part of the training set initially. Then actually this retrieval augmented generation approach is super, super popular right now. It's also, I would say, pretty easy to implement, even if you don't really know that much about large language models and all the mathematics behind it. In the demo here, I will show the last out of those use cases. So I took the documentation from Ivan platform, and I used that as additional context. And then I provided that context in a form of vectors to large language model, and then I asked some boring, no cats or dogs in this demo, I'm sorry, but some boring questions. And the whole architecture here used AWS. Okay, not exactly open source, but this demo, I think it's like OpenSearch is an open source technology, and the rest you can actually replace with your own approach. And we have two parts of this architecture. The first one is data ingestion, and it's very similar to what we have seen so far. When we get the data, we then use some model, we produce some embeddings, and we store that in a database. And I store it again in OpenSearch over here. And we have the second part where we actually then use the large language model to send the prompt. But in addition to prompt, we also add the context. And then we actually ask the large language model to pay some additional attention to that context that we are adding. So for this one, I used the SAM templates, the serverless part. If you're experimenting, I would, you can run the SageMaker model, but running something serverless on AWS for experiment is way, way cheaper. So again, depends on at which stage you are, but the difference in the bills I get is day and night. So then let's look at the first part, is the data ingestion. And what happens here, so what I did, I had an S3 bucket, and then I was putting there the documentation files from Ivan platform. And then when an item was arriving there to S3 bucket, I was triggering an event notification and putting the data into a queue. And then after that, I was triggering Lambda function. And in that Lambda function, I was using the LangChain library to work with that data. Here, code again is kind of minimalistic. I mean, of course, for production, you will have to do way more coding. But for to make it work, you don't really need to know a lot of things in depth, because LangChain will take almost all of that thinking on itself. And here I'm using the Bedrock model from AWS to get me embeddings, and I'm actually again LangChain knows how to work with Bedrock. LangChain knows how to work with OpenSearch, and you can actually check there is a lot of support of different external those elements. So whatever you use, you need to verify that LangChain supports that, but it supports a lot. And in the end, I'm connecting to the Bedrock, I'm connecting to OpenSearch, providing that information to LangChain, and sends okay, please process this piece of information, get me embeddings, and store it in OpenSearch. And if I look at OpenSearch while I'm doing this, I can see that the index is being populated with the data. And I'm getting like information about the embedding and information about like the content of the document which I'm using. Yeah, so this is kind of part which we have seen before, but using a bit more of the long chain. The second part is like to get the data retrieval, and here to rely on large language model. So I have another Lambda, and in this Lambda, okay, the first Lambda I had in Python. And I was like, I should be consistent, but the problem is here I wanted to use, like with Lambda, with AWS, I wanted to use a streamified response, which kind of can chain me the response and retrieve it in pieces, like when you see chatbot or ChatGPT talking to you, it gives you like small snippets because it kind of takes time to produce those. So I wanted to have the same, but it's only Lambda which uses JavaScript supports that. So we are here using some JavaScript code, and then here in the body of the function of Lambda, again, I'm connecting both to Bedrock, but also I'm using the large language model. I create the prompt. I specify there that please use the context, and then whatever event comes from the user or whatever user interface you have, I put the question there, and then I create the chain, and then return that information to the user. So like the long chain will take information from the OpenSearch. Again, like this is like kind of where, I don't know like if I like it so much, but long chain actually hides all the complexity. So you need really like to know how to work with it. I kind of always prefer to know a bit more like actions when I see what exactly I'm doing. But this is like, it's totally like behind the scenes. It does the connections to Bedrock, to OpenSearch, combines it, how it sees the best, and then returns the result. Oops, I missed, I need to go back. And then I get this kind of, I use just here the curl and access Lambda directly, which probably not the best thing to do, but you probably want to add some kind of interface and so on. So yeah, so this is how this works. The disadvantage, at least for my particular demo, I didn't have so much documents, so the context was limited. So you want actually probably, if you are given the additional context, it should be something like significant. Otherwise, you also have hallucinations. So kind of we actually use this additional context to decrease the number of hallucinations for certain topics. But again, if you're providing the context and it's also kind of not big enough, you're getting also a problem of hallucinations. So, but in any case, this actually works pretty well still, and you can apply it for your projects. Yes, for all of those demos which I have shown, we are creating the embeddings. And for those of you who actually already worked with vector search, I guess that you know which model to take and how to work with it. But for those of you who actually just starting to work with it, I wanted to give just maybe like a guidance on the easy start, where you don't really, like, kind of it's a bit easier to begin. And you raised, like, you raised a hand when I asked about Python. So I love Java, I love JavaScript, but with Python, things are just way easier. Like you can use different models with Hugging Face. If you don't really know so much Python, you take the code and you can run that model. If you really want to use Java or JavaScript, TensorFlow is the model, like the sentence encoder in TensorFlow will work. It's a bit more limited. You don't have so many models there, but it's actually also kind of a solution. It can be also that you don't really want to run the model on your own, and it's also totally fine because you can use APIs. Here is kind of an advantage because you can focus only on your functionality, and then you can use Hugging Face API, OpenAI. You can deploy stuff to SageMaker or use, I don't know, Microsoft, Google platforms. You can use Bedrock, like, so different options. The disadvantage is that if you're just starting and experimenting, even though it's not expensive, but you will have to kind of create your account and put some money on those systems. In the past, Hugging Face was very friendly with kind of API which I could use for free on the limited number of calls, but I think that they were not really super transparent on number of calls you can use, so it was a bit kind of weird, but it was still working. But now I think they're shrinking that usage, so I can't really, at least like for me, it doesn't really work anymore. So maybe we'll have some kind of a free tier options with those platforms soon, but so far that's what we have. Then for the retrieval augmented generation, LangChain supports, like it was by default with JavaScript and Python, but there is a really good solid support for Java, so that one you can use with Java. Also, the interesting thing, like with Hugging Face, if you ever decide to deploy a model to SageMaker, for example, that actually is pretty straightforward, even if you don't really know much, neither AWS nor Python, because they offer the code. You just copy the code, like in the deploy versions, the deploy code snippets. You can check that, and it actually works out of the box. You put it either in the notebook or in the code space, which they have in SageMaker. But again, be careful here, because that can actually, like if you use it for just experimentations, stop the model, stop the endpoint after that, because it actually gets very expensive very, 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 very fast. So yeah, and don't ask me how I know. So then if you have an endpoint there, like with Java, you just work normally using that endpoint from your code and invoking that endpoint. So, oh my God, I talk so fast because we started so late, but I hope that was still digestible. So I do have a couple of links to share. I was sharing those several databases. You can get, like this gives you some extra credit, and we have a Postgres free tier, which you can use, and that will work. We have like PG vector installed there, so you can use it as it is. And we have not only those databases, but a lot of others, and that number of credits you get should be sufficient to experiment with many different solutions. Then I also want to leave, this will bring you to all the repositories for different demos, which I showed, at least, yeah, okay, the ClickHouse just was very, very simple, but the rest I have the code, and I tried to also like to kind of add the descriptions everywhere, so it should be kind of, I hope it should be okay to follow, like I really try to put effort into making it very digestible. Yes, so that's the information from me. I don't know, we don't have so much time, but if you have a couple of questions and they're not kicking me out, then we can go for those questions.
A quick question about the data set. We know that the security of the data, is there something that we need to consider that the data gets exposed to those public services?
Yeah, the question is about the security of the data set. So don't use data which you don't know. I mean, like usually for those things, both model and data, you need to know that you can trust it. But data, I assume, will come, for example, you have the reviews for your product coming from the user, so you kind of know that you have the data. You might actually use some models if you want to process the data and publish somewhere. You can actually use the model which will look for the all nasty stuff. And I worked with some social media stuff, like you can actually filter that one, but it will be your data. So I kind of feel that the data you take, usually you kind of, it's your data, so you can trust it, unless you use some kind of third-party data, but then you need really like maybe to pre-process it.
Maybe master data or something, replace data with some fake values, maybe that's similar in value.
You mean like, okay, you mean that like for the...
I guess you can do something like that for security reasons. Let's say you have names and maybe flip names.
Yeah, okay, of course, like totally, like I'm from Germany, so like with GDPR and stuff, you never want to use a personalized information like this. And yes, then you need to be careful. Then you want to kind of process the data, maybe kick out like the names of people which you don't really need to have, and only leave what you want to have there. Cool. I'll be here around, so happy to talk more about vector search. And thank you so much for coming to the session. See you.